Hello everyone, welcome to this 10th lecture of the NPTEL course in Riemannian geometry. So last time we talked about isometries between Riemannian manifolds. So let me just quickly remind you what the definition was. So we take two Riemannian manifolds necessarily of the same dimension n, then a map from M to N is said to be a local isometry if it is a local diffeomorphism and it satisfies this equation, the metrics satisfy this equation. So the metric on M is a pullback of the metric on N, and we say that it is a global isometry if F is a global diffeomorphism, right, and it continues to of course satisfy this equation. So then last lecture we also saw that these three Riemannian manifolds that we had introduced in I think lecture 8, they all turn out to be isometric, right. So the hyperbolic space, the Poincare ball and the Poincare upper half, they all turn out to be isometric to each other. So the aim of today's lecture is to discuss another large class of important examples, namely tori, and actually to be more precise, flat tori. Okay. So the aim of today's lecture is to talk about flat tori. Okay, so recall that Rn being a vector space is of course forms a group under addition, right. So here is a definition. I want to look at particular kinds of subgroups of Rn. So lattice L is basically a discrete subgroup of Rn such that if you look at the span, so we want it to be a full rank, which means that if you look at the span of L, which by definition is simply the collection of all vectors in Rn, which can be written as Ti times Vi, some finite linear combinations of Vi's, where Ti is some real number and Vi is an element in L. So if you take the finite linear combinations of R linear combinations of elements in L, that spans the entire Rn. Okay, and then a fact that is not too difficult to check is that given any lattice, there exists vectors omega 1 to omega n such that the lattice is simply given by z multiplied by omega I. Okay, where z is as usual the set of integers. So in other words, this is basically the set of all linear combinations of the type Ni, or maybe let me use Mi, omega I, where Mi are now integers. So in other words, as groups, this L is just isomorphic to Zn, right. Okay, so now of course there is an action of L on Rn by translations. So one can take the quotient under this action. So we define this object TL to simply be the quotient of Rn by this. So because L is a discrete group and the action is fixed point free, there exists a unique smooth structure on TL such that if you look at the natural projection map pi L from Rn to TL, this is a smooth covering map. Okay. So let me just draw maybe a picture. So so let's draw a picture in n equals 2. So let's say my so here the lattice is generated by just two vectors. So let's say my omega 1 lies along the x axis and omega 2 is this vector here. Right, so then this will sort of tile Rn, just translations. Translations by these two vectors will basically tile Rn by these parallelograms. Okay, so I look at this parallelogram which is called the fundamental parallelogram of this lattice. So the fundamental parallelogram will be this. So this is denoted by PL, that's just the set of linear combinations Ti omega I such that now Ti is only between 0 and 1. Okay, so this is called the fundamental parallelogram. So then topologically, what is this torus TL? What you are essentially doing, you have this famous picture. You are basically taking these two edges and these two edges and gluing them together. So if you glue these together, you basically get the familiar picture of a torus, namely a donut. Sorry. Okay, where these blue edges are will give you a circle, and these pink, identifying these pink edges will give you another circle, right? Okay, so this is basically your torus TL. So this TL is called a torus. Okay. All right. So the first observation is that topologically, or at least diffeomorphically, all of these tori are actually the same. So TL is diffeomorphic to simply a product of n cross product of circles. Okay, so what is the proof here? It's elementary, so let me quickly repeat it. So consider the following map from Rn to an n-fold product of circles. So any point, because omega i's form a basis, any point in Rn can be written in this form. So then I simply send it to the point on the circle represented by this tuple. Okay. Then clearly phi tilde is invariant under the action of L. Why? Because if you modify these coefficients by an integer, then the effect here is that you multiply by 2 pi I times some integer, but 2 pi I times some integer is just 1, right? So clearly phi tilde is invariant under the action of L. So that means it induces a map from the torus to this, and one can easily check that this is a diffeomorphism, right? One can explicitly construct the inverse. So at least as far as the smooth category is concerned, all these tori are identical. But now since this is a course in Riemannian geometry, I want to actually introduce a Riemannian metric on this. So our goal okay, we do this in the following way. So again, let me write that as an observation. If you look at the Euclidean metric, this is translation invariant. So that means it will induce a metric which I will denote by GT, sorry, GL on this torus TL. So let me draw a picture to explain what is really happening. So again, let's draw this picture of Rn being tiled by these parallelograms. So the fundamental parallelogram was this thing, right? This was PL. Now the idea is that PL covers almost the entire torus. So it's enough to actually describe the metric on PL, and in fact you can cover the torus with two such coordinate charts which are isomorphic to this fundamental parallelogram. So it's enough to describe what the metric looks like on the fundamental parallelogram. So if let's say you are working at this point and you have two tangent vectors here, right? So then they will correspond to two tangent vectors in Rn, right? And in fact it does not matter, I mean you can think of these as vectors either here or in this parallelogram or in this parallelogram and so on, right? But because the metric is translation invariant, the inner product between these two, the inner product between all these vectors is basically the same, all these pairs of vectors, right? Because the metric is translation invariant. So you just define the inner product of these by computing the inner product here. That's essentially the definition of TL. So I'm not going to, I mean soon enough I'll write explicitly what this metric looks like, but for now I hope I've convinced you that there is a very natural way of defining a metric on the torus, and in fact GL is the unique metric such that pi L, which was, remember this natural projection from Rn to TL, is a local isometry. So because it's a covering map, it's a smooth covering map, it's already a local diffeomorphism. But now with this new metric that I have defined on the torus, it actually becomes an isometry, i.e. if you pull back GL by pi L star, then that is just the Euclidean metric, okay. And in fact with this condition GL is the unique such metric. Okay. All right. So now I want to write this in local, so explicit form. Okay. So so note that you have your fundamental parallelogram PL, and PL can be identified as an open subset inside TL, right. So in fact I had drawn this picture of the donut. You have these two circles. So in fact the interior, sorry, so when I say PL, I should say the interior PL. The interior PL is basically just the complement of these two circles in the torus. So that will give you an open set in TL, and now I can actually give a coordinate chart on this PL, which maps into a standard parallelogram, which I will denote by Q. So Q is basically the summation of Ti Ei, where Ei is now the standard basis. This is the standard Cartesian basis. Okay. So so it's easier to write down a formula for the inverse image of phi. So the inverse image of phi will take an arbitrary point T1 with coordinates T1 up to Tn here and map it to this point whose coordinates which is basically given by summation of Ti omega I. Okay. So now the goal is to express GL in terms of these coordinates T1 up to Tn. Okay. All right. So in order to do that, we just notice that if you look at the tangent vector in the ith direction, by just differentiating this inverse map, this is clearly the same as omega I. Okay, which means that if you take GL and take the ijth component, which is of course del Ti by del Tj, then that's just going to be omega I omega j, where now you are using the Euclidean metric. Why? Because by definition GL is basically just the Euclidean metric on this fundamental parallelogram. GL is just the Euclidean metric. So that is why here we are just using the Euclidean metric. Okay. All right. So that means we have the following explicit formula, that GL is given by summation I going I and j going from 1 to n omega I omega j times dTi tensor dTj. Okay. All right. So yeah, let me sort of clean this. Let me write this in a better way. So this is summation I j going from 1 to n omega I omega j dTi tensor dTj. All right. So finally, what I want to do is the following. So a natural question is whether you look at the Riemannian manifolds, let's say TL and GL and TL prime and GL prime, are they genuinely different Riemannian manifolds? So when I say different, that means are they not isometric to each other? So, or are they isometric? Okay. So it turns out, so I will write this as a sort of proposition. So let L prime be lattices of full rank, be lattices as above, then the Riemannian manifold TL GL is isometric to the Riemannian manifold TL prime GL prime if and only if there exists an orthogonal matrix which takes one lattice to the other. Okay. So in particular, as an example, let us say you take L to be Q and L prime to be generated by 1 and zeta 3, where zeta 3 is the cube root of unity, right. So let me just draw a picture. So this is Q, and this is the lattice formed by L prime. Then the corresponding Riemannian manifolds cannot be isometric. Why? Because there cannot be an orthogonal transformation taking the lattice L to the lattice L prime, because orthogonal transformations preserve angles. The angle in this lattice is the angle between two basis vectors is 90 degrees, whereas here it will be 60 degrees. Okay, so there cannot be so these are two genuinely different Riemannian manifolds. So let me outline a proof. I won't write down all the details, but hopefully there is enough that you can work out the details for yourselves. So it's an if and only if statement. So let's first prove the reverse implication, that is, suppose there is an orthogonal transformation which takes L to L prime, then I want to claim that that these two are isometric, but then let L be generated by this basis omega 1 to omega n, and let L prime be generated by this basis omega 1 prime to omega n prime, such that because A takes L to L prime, I can always choose this basis so that omega j prime is simply omega applied to is simply A applied to omega j, right. But then by our explicit formula, what is GL prime? That is the summation over Ij of omega I prime inner product omega j prime. This is the inner product in Rn, dti tensored dtj, but that is the same as A applied to omega I times A applied to omega j. But because A is an orthogonal matrix, this is the same as omega I omega j dTi tensored with dTj, which is GL. Okay, so these two Riemannian metrics coincide, and hence the corresponding Riemannian tori are isometric. So now let's prove the forward direction. So let capital F be an isometry. So then by it's a general fact, because Rn is simply connected, it's the universal cover of these tori. So by general covering space theory, so this sort of thing is covered in any sort of basic course in topology, or maybe first course in algebraic topology. There exists a unique f tilde from Rn to Rn satisfying this normalization that it sends 0 to 0, such that the following diagram commutes. So you have Rn to Rn, you have your pi down to TL, you have your isometry f here, and you have pi prime here, right? So you want this diagram to commute, which means that that this should be the same as this. So if you write it out, it basically means that pi prime composed with f tilde is the same as f composed with pi. Okay. So now the claim is that f is a local, f tilde, the lifted map, so f tilde is called the lifted map, is a local isometry. Okay, the proof is not very difficult. You just trace through by chain rule. At any point P in Rn, you basically have the d pi prime at f tilde of P composed with d f tilde at P is the same as df at pi of P composed with d pi at P. Okay. But now, because pi prime is a local diffeo, this map, which goes from the tangent space of f tilde P of Rn at f tilde P to the tangent space of pi prime composed with f tilde of P of the torus, this is an isomorphism. As a linear map, this is an isomorphism. So one can define its inverse. So that means that this map is well defined. But by definition, each one of these maps is an isometry at the level of the tangent spaces, right? Because each of these maps, pi prime, pi and f, are local isometries with respect to the correct Riemannian matrix, right? So this implies that so this going from the tangent space to Rn at P to the tangent space to Rn at F tilde P is an isometry. Which in turn implies that that F tilde is a local isometry. Why? Because the fact that it's an isometry means that the kernel in particular of this map is never vanishing. Then by the inverse function theorem, F tilde has to be a local diffeomorphism, right? So in particular, it's a local isometry. But now you can do the same with the inverse map. So now consider the inverse map G inverse, inverse map G equal to F inverse, which goes the other way. So from this, by the same construction as before, we obtain a map G tilde, which is a local isometry, and in fact one can easily check that that this is the identity, which means that the F tilde is a diffeo, and hence F tilde belongs to the isometry group of Rn. But then this implies that by the theorem that I wrote down yesterday, that or the previous lecture, that F tilde is given by an affine linear map where A is an orthogonal matrix and B is some vector in Rn. But now by my normalization, F tilde of 0 is 0. This implies that B is 0, which in turn implies that F tilde is basically given by an orthogonal matrix. Okay, but then if F tilde is given by an orthogonal matrix, F tilde ought to take the lattice L to itself. So this implies that A takes the lattice L to L prime. Okay. Sorry, I meant that F tilde being a lift of F actually takes the lattice L to L prime, which just means that A takes the lattice L to L prime, which completes the proof of our theorem. Okay. Alright, so maybe I'll end this lecture with the following remark, that more generally suppose you take L to be G to be a discrete subgroup, such that the action on M is fixed point free, then there exists a unique maybe I'll denote it by a unique metric H on the quotient. So because G is a discrete subgroup which acts without any fixed points, the quotient has a natural smooth structure such that if you look at the quotient map, then pi star of H is precisely G. So the quotient map becomes a local isometry. Okay. Alright, so that's it. That's it for today. So this essentially finishes our sort of basic discussion of Riemannian manifolds. In the next lecture I'll discuss some, in the next couple of lectures I'll discuss some basic constructions regarding Riemannian manifolds, and then we can move on to more advanced topics such as connections, curvature and so on. Okay, so that's it for this lecture. Thanks for the attention, and I'll see you next time around. Thank you.